Welcome to the group report for Group 18. In this video, we'll be discussing and showing all working features of the Network Traffic Simulator. Starting with the first basic feature, the Network Traffic Simulator takes input from the user in the console. It also deals with error handling, making sure all input is uniform and validated. A quit command was also implemented to ensure graceful exiting of the program. Let's now discuss the traffic model implementation. The traffic model is built around the event class, which holds a timestamp, an event type, and a source ID. The event type enum is used to determine whether a source is turned on or off. Event durations are sampled from a heavy-tailed Pareto distribution. Aggregate rate is calculated by tallying the number of active sources. Let's now discuss the event-driven simulation. The event-driven simulation is run through a Simulation Manager class. The Simulation Manager uses a priority queue to process events chronologically. By implementing the comparable interface, this allows each event to be compared based on its timestamp. Let's now move on to simulation execution. The user is prompted to enter a time duration to run the simulation for. The input is then stored in a variable and used to execute the run function, which runs the simulator until the time elapses. The run method grabs the event at the top of the priority queue and calls the handle function. The handle function processes events based on its event type. It also adjusts the aggregate rate based on whether the source is on or off. Let's now talk about the output of the simulator. Each time an event is processed, the time and the total aggregate rate at that time are tracked and logged to a CSV file. More descriptive data points, such as the source ID and event type, are also tracked and logged to a separate CSV file. Summary statistics are also tracked, and then once the simulation completes, they are logged to a third CSV file. Let's revisit briefly how the user interacts with the console. The console prompts the user to enter simulation parameters such as time, number of sources, and Pareto distribution parameters. Once the simulation starts running, it prompts the user with update messages. Let's briefly discuss graceful exiting using the quit command. Each time input is entered by the user, this input is checked by the system to verify if it is or isn't a quit command. If the command is quit, this exits the system. If not, other checks such as whether input is string, integer, or double is then run by the system. Let's discuss how the system deals with incorrect input by the user. The system implements robust error handling, making sure to test for all edge cases and misformatted input by the user. When input is entered incorrectly, the user is re-prompted with the same prompt before, but with a helpful error message stating where they went wrong. When default cases are triggered in the case of invalid input, this is made sure to be aware for the user. Let's now move on to the first advanced feature, which is loading parameters from a file. The simulator config loader and the load from file method are used to take in a file path string and parse a file of the following format. The file parameters are then ingested into the system. The next advanced feature is outputting results to a CSV format. This was already covered in Basic Feature 5. No output is done to the terminal except for progress loading messages, and all simulation results are logged to individual CSV files. Let's now discuss the basic network queue. The simple queue class models a basic network buffer. At each simulation step, incoming packets are added, and if the buffer is full, the extra packets are counted as dropped. The queue then drains at a fixed service rate, simulating a network node processing traffic. This lets us observe congestion effects like queue buildup and packet loss, which are logged to CSV files. Let's now discuss estimating the Hurst parameter. The Hurst estimator class measures how self-similar or bursty the network traffic is. It takes the simulation time series data and applies rescaled range analysis. This is done over multiple window sizes to capture long-range behavior. The results are transformed using log-log scaling. Finally, a linear regression is applied and the slope gives the Hurst exponent. Let's now discuss fractional Gaussian noise. The FGN generator class generates fractional Gaussian noise to model self-similar network traffic. The Hurst parameter controls the level of long-range dependence in the traffic. A full sequence of noise values are generated once the simulator starts. The generator first computes the autocovariance function of the fractional Gaussian noise. A Hosking recursion is then used to generate correlated samples. Each new value depends on previous values plus Gaussian noise. During the simulation, values are returned sequentially to drive the traffic behavior. Let's now discuss how this system was tested. Each major class was tested using JUnit testing, making sure to catch all edge cases and ensure system functionality. 100% test coverage was aimed for, however, due to the nature of the input handler class, which requires user input, as well as testing for getters and setters, some classes did not receive 100% test coverage. This is now the end of the video report for Group 18. Thank you very much.